here on my computer. That should now be recording, yes? Okay, great. Here's a small outline of some of the things that I intend to talk about today with you. It's a little bit cryptic, I know, that's intentional. So I will start off while you are digesting your lunch or still eating your lunch with a soft intro on just some interesting trends in the energy transition that I think are worth sharing, and again, that energy economists pay attention to. I'll talk about a machine, about the role of electricity in the energy transition, which is also my main focus, electricity markets, electricity systems. I'll talk about trading electricity, electricity markets, how do they work? That's, I think, the most important part, also the most challenging part of what I'm going to talk about. And if we still have time, I'll briefly touch upon the controversial topic of, do we still need fossil-fueled electricity power plants, namely gas-powered plants? So starting off with some trends in the energy transition. Quick 1-minute summary of climate science. I like to compare our atmosphere with a glass of water. And the CO2 emissions with a liquid like a grenadine, which you might know, kind of a syrup to sweeten your water, right? So what we do is we fill our atmosphere with more and more of this grenadine, these emissions, and what happens, the concentration of grenadine in the water increases, right? The water becomes sweeter and sweeter, and so the concentration of CO2 in the atmosphere globally increases, right? You're aware of this. As you continue to pour, the sweetness of the water increases, the concentration increases. And so to make the analogy complete, in our atmosphere, the grenadine is our different sources of emissions. Our industry, transport, our houses frequently have emissions coming straight out of them. And so these pour into the atmosphere, increasing its sweetness, if you will, increasing its concentration of emissions, and that's what, of course, leads to the increasing temperature that we all know about. Always good to have a quick refresher on where global emissions are headed. Since the 90s, before you were born, I assume, emissions have continued to rise, and over the past couple of years, they've sort of plateaued, not yet really coming down on a global level. The one thing that did make them go down in a significant way was the pandemic and the fact that lots of factories were closed, lots of lockdowns. That was actually the first time in recent history that global emissions took a big dip. And when this was over, as you can see in the last point on the figure here, emissions climbed back to where they were. So we're currently around the plateauing part of hopefully the mountain, so to speak, after which we will go down. Now, to give a bit more insight on where these emissions are coming from, literally where, in the sense of geographically where, this chart shows you in colors which countries are responsible for most of the emissions. And again, apologies for not being able to show these slides all the way on the television screens in the back, but the red here depicts China, India in yellow, North America in green, and then here at the bottom you see the EU 27's part of global emissions. So we have been going down slowly but steadily since the 90s, but of course other countries have sharply risen, and so this is where we are today. And hopefully we are now about to make the bend downwards. You can also show this same. Okay, never mind that. So what's happened to emissions, to the syrup in the atmosphere, to the sweetness of the atmosphere, the concentration? This curve might be familiar to you, the hockey stick curve, it's sometimes called, because of the large vertical here on the right. This shows actually how the concentration of CO2 emissions has evolved in the Earth's climate for almost the past 1 million years, so 800,000 years. And so you can see it's been sort of fluctuating a bit depending on what happens, ice ages and what have you. And it's been fluctuating between 200 and 250. And in the very recent past, so this is sort of all of modern society, we've jumped to a much higher concentration of emissions in our global atmospheres. And as I previously said, this leads to these global increases in temperature, where we see that today we are already at an increase compared to pre-industrial times of 1 degree. Doesn't sound like much, but when you're talking about global average temperatures, 1 degree is a lot. All the things you already see today in terms of climate change, climate impacts, are the result of this 1 degree that we're at right now. And the ambition globally, as you're all aware, I assume, is to remain between, remain at least below 2 degrees, and hopefully lower than that, to not go beyond 1.5 degrees. Good. So that was a couple of minutes on climate, which serves as a background for the rest that I'm going to talk about. What do we need to do now about this temperature rise, this climate change? We need an energy transition, right? And the energy transition that we are currently in the middle of, or in the initiating phase of, is not the first energy transition. Historically, other energy transitions have taken place, and what's shown here is one of those previous energy transitions that have happened in the world. Namely, it used to be the case a long time ago that 100% of the energy used by human beings came from wood, burning wood. It was the only thing we had. In terms of energy use, we went to a forest or whatever to collect something that burns, burn it maybe to cook on or to heat our homes. And we transitioned away from that. An energy transition took place, and that took about 200 years, from the year 1800 until 2015 is where this figure ends. You can see that over time, wood became a much smaller part of our overall energy use. There's still some use of wood, globally speaking, right? Especially in some of the developing areas of the world. A lot of people still collect wood and use it to cook. But something else replaced wood almost entirely, which is, of course, fossil fuels. At first, in dark brown, we discovered coal. Coal under the ground, fossilized wood and dinosaurs, etc. And that quickly grew and became a big source of energy in our human societies. After which then natural gas and oil were also entering the scene, and each grew themselves. So today, or roughly today, we have a global energy mix that is mostly fossil fuels, coal, oil, gas, natural gas, and a bit of other things that we want to heavily increase now and make the fossil fuels go away. And in black here, it's probably not even visible from the back. In black is wind and solar, for example, at the moment. In the year 2015, not really at the moment, almost 10 years ago. So the black part's about twice as big now, but it's a sliver. We have a large job to do to scale this up globally, to replace all of this. And so the question becomes, is this going to take another 200 years like the previous energy transition? Hopefully not, because we are told by climate science that we have about 20 years, 10 years, 30 years left to do this job globally. And so that's what I would like to continue talking about in my next slides. There's always going to be a couple of people that do not believe at all that we are going to succeed in this, that do not believe at all in certain big changes taking place. And one example of this that has nothing to do with energy, but it's just a nice example to give, was the previous CEO of Microsoft, the tech company, who said in 2007, I remember this myself, I was 17 at the time, the first iPhone came out, and it was a very expensive device compared to other things that were available on the market at the time. And he said there's no way, no chance at all that this is going to gain market share and become a big thing. He really didn't believe that at all. He saw this overpriced device which you have to touch with your fingers, and he didn't believe at all that this huge change that then actually happened was going to happen. It's just an example to give out of the energy world. But of course, there's some nice examples in the energy world as well. Here, for example, you see a page out of a newspaper in Germany in the early 90s, 1993. Renewables were starting to become a thing. The first windmills started to be built, etc. Some solar panels started to appear in the German landscape. And a big group of experts in the electricity system, electricity experts, they said in this newspaper ad that it was by definition impossible to have more than a few percent of these renewables in the electricity system. And they had all kinds of technical reasons to explain that it was impossible to keep this delicate electricity system working when you would have wind and solar as a part of it. So only a very small percentage would be technically possible according to them in 1993. And remember, these were the best experts. And last year, more than half of all electricity in Germany came from wind and sun. So they were wrong. And so this is just to give you an idea of how people, including experts, may have a very difficult time to be able to estimate the degree to which big changes are actually possible in the short term. So this energy transition question of does it need to take 200 years again, as it did last time, it's hard to judge. And you have believers and non-believers. And hopefully in 20 years, I'll be able to show a slide like this, showing that, in fact, the non-believers were wrong. But still to be seen, of course. A few pictures then, just to give you an idea of, okay, where are we actually headed? What is actually happening so far? Here you see recent changes in the electricity mix in the United Kingdom. And you see that before the year 1960, about here in the middle of the graph, all of the electricity generated in the UK came from coal, burning coal. After that, they started building nuclear plants in green, which replaced some of the coal, and they started building natural gas-based power plants in purple. And recently, wind, hydro, solar, renewable sources of electricity became a thing in the UK. And today we see that in the span of a couple of decades, coal that used to be 100% of electricity generation, pretty much, was completely replaced. There is today zero coal generation in the United Kingdom. We have there a mix of nuclear gas and more renewables, which are very quickly growing in the UK, especially offshore wind, so windmills that are built in the sea are becoming bigger and bigger every year in the UK. So this already gives you an idea. Okay, in terms of generating electricity, at least in this one country, apparently you can have very big changes in a couple of decades. This is the same country, same time period, but instead of showing the spread across the full range, so the full 100%, as it was on my previous slide, this figure shows at the same time how the total use of electricity, the total consumption of electricity increased in the United Kingdom, right? So it doesn't just show you the mix, but you can also see in this figure that the total amount of electricity generated grew by a lot, right? In that same period. The peak amount of electricity consumed in the UK was around the year 2000. Right now, that's sort of decreasing year after year as we have more and more efficient appliances, light bulbs, fridges, all those things are becoming more efficient. So total electricity use has been going down in the previous decade in the UK. Whether or not this remains the case, this decrease continuing is a question mark, because as I'll come back to later, we're also going to do more and more with electricity. We're going to use electricity for things that we did not use electricity for before, like driving cars. Instead of using oil, driving them with electricity, heating our homes. Instead of burning gas, using electricity to drive a heat pump, right? So probably this will tend to go up again. And then we hope that the blue part will take in more and more of the remaining area. Germany, also some big changes happened there recently in the last 20 years. You can see that in Germany, a lot of electricity was generated with coal power, two varieties, brown coal and regular coal. Brown coal is also called lignite. And while this has been decreasing in the past couple of years, at the same time, the amount of electricity generated from wind and solar power in Germany has heavily increased. And you can have all kinds of hours-long discussions about whether they are taking the right approach in Germany, because the amount of coal power being generated still today is quite high, and it could be almost zero if they did not decide to phase out nuclear electricity, which they also did. Different discussion that I won't go into today, but in any case, the picture is meant to show big changes are possible in a couple of decades. At the European level, you can also take a look. In the year 2020, it happened for the first time, and now this just occurs every year, that more electricity was generated from renewable sources in Europe as a whole than from fossil fuels. And at renewables, remember, that's not just wind and sun, it's also hydro, so water power coming from dams, etc., or rivers, and biomass, so basically burning sustainable sourced wood. That's all in renewables. If you only look at wind and solar at the European level, that also jumped ahead, particularly ahead of coal for the first time in the year 2020. So today and then from now on, every year it's the case that in Europe, the amount of electricity coming from the wind and the sun is more than the amount of electricity coming from coal power plants. So these are some encouraging lines at the European level. Then enough about electricity generation. How about some other parts of the energy transition, like transport, right? We don't only need to make sure that our way of producing electricity becomes zero carbon, but also that our way of moving around becomes zero carbon. So how do we move ourselves around? There are a lot of cars in the world. There are always going to be a lot of cars in the world. Also, if in cities like Ghent, we take measures which are fine to make people use cars less in the city environment. But we're not going to go to zero cars on a global scale, obviously, also not in the next couple of decades. So the cars that we will still have will have to not emit anymore. And how's that going? That's what's shown on the slide. The sales of electric vehicles. How has this changed in the previous 10 years? As you can see, 10 years ago in 2013, there were basically no electric cars being sold in the world. And last year, more than 10 million were sold. And you can see where this is going. Probably this 10 million bar is going to look super small in another 10 years because it's going to be 100 million. This is rising exponentially. So, okay, big changes occurring in a matter of a few years, electrifying the way we move around in cars. And in fact, by the way, if you don't notice, there are plenty of places now around the world that have deadlines for fossil-fueled cars, in the sense that they say, these are all examples shown on the slide of cities that say, after year X, 2030 or 2040 or 35 in some cases, we do not allow fossil-fueled cars to enter our city anymore. Or we don't allow fossil-fueled cars to be sold anymore. So this is happening in a very, very fast way. Globally, the collection of places where you're just simply not welcome anymore or cannot buy a fossil car anymore, right? Not welcome with a fossil car or cannot buy one anymore. That's growing quite fast, especially as you can see in the richer parts of the world, but also including China and even South Africa, sorry. You can also talk about the energy transition that's occurring globally at the moment in terms of money. Just purely, okay, on a global level, how much money is being invested in green stuff every year? And last year, globally, this reached 1 trillion for the first time. So in 1 year, the year 2022, $1 million was invested in the energy transition, you could say. And as this slide, it's not actually mine, it's from a person called Ned Bullard. As he titled it, the first trillion is the hardest. So what he intends to say with that is this previous period of ramping up the amount of money we invest in the energy transition, that was actually the harder part. And from now on, presumably, every next year, we are going to continue to invest trillions on a global level in the energy transition. Now, it may be a bit abstract to you, right? What's this money going to? What does that mean, $1 trillion invested? Well, this slide shows what's sort of behind those numbers. You can see that about 500 billion was invested last year alone, globally, in renewable energy. So that means when you build a new windmill, and it costs you 1 million euros to build it last year, that's 1 million invested in renewable energy last year, right? And so if you add up every dollar that went into building a new windmill, building a new solar panel somewhere, that was 500 billion last year, sharply increasing year over year. And a lot of billions also, went to new electric cars. So we can discuss about that, whether it's a good metric. So, but every time someone buys a new electric car, when we look at that, for example, in the year 2022, every dollar that went to buying a new electric car is seen here as an investment in the energy transition. So about, what was it, 10 million electric cars times a price of, I don't know, $40,000 or $30,000 per car, and you get millions and billions of dollars invested in the energy transition. And there are also investments happening in other things, but those are comparatively small at the moment. So you have here, for example, investments in new nuclear power plants in China and other places, investments in hydrogen, which are actually almost invisible here on the figure. But globally, $1 trillion invested last year, not bad, and this is continuing to grow year over year. So big changes are possible. And one of the things that makes the increasing investments possible in particularly solar energy is the fact that it becomes cheaper and cheaper every year. And this is, in fact, of course, a feedback loop. It's because we're investing so much in it that it becomes cheaper, which makes it easier to do even more of it, which makes it even cheaper, and so forth. What does this figure show? It shows how the price of a solar panel has dropped since the year 1976 until a couple of years ago. What this figure basically shows is that as you install more and more solar panels, they tend to get cheaper. That is called a learning effect, and this kind of a figure depicts a learning rate, a speed of learning, if you will. Solar panels have demonstrated over the past couple of decades that they have a learning rate of 20%. What does that mean, a learning rate of 20%? It means that every time that we double the amount of solar panels that have been built ever in history, every time that amount doubles, solar panels tend to become 20% cheaper, right? So in the beginning, in the 70s, we had almost no solar panels. Let's just for the sake of argument, say we had 1,000 solar panels in the world. We built a few more. Then at some point we had 2,000 solar panels. After doing that, solar panels were 20% cheaper because we built more of them, learned some things about how to manufacture them in a more efficient way. We doubled again the amount of solar panels in the world from 2,000 to 4,000, and again they were 20% cheaper. And so you can imagine if you keep doubling, it gets exponentially harder because at the moment we have already so many of them that, again, doubling the total amount globally takes a lot of factories and a lot of effort, a lot of solar panels. But amazingly, we see time and time again over all of these years since the 70s that this learning rate of 20% keeps happening. And so it's incredibly steady. It's a sort of an energy economics observation, studying just what's happening in reality on the ground. And so we can expect this learning rate effect to keep occurring as we keep on doubling the amount of solar panels in the world. And the same is true, by the way, for other technologies, renewable technologies like onshore wind, windmills on shore, yeah, not in the ocean, and offshore wind. They each have their own learning rates that have been observed historically. They tend to get cheaper, although at different speeds. So not every technology becomes 20% cheaper every time it doubles. Each technology has its own learning rate, its own speed of getting cheaper as you build more of it. Nuclear energy, by the way, does not have a learning rate that we can observe so far. As we've built more nuclear energy over the past decades globally, it has become more expensive instead of less expensive. So in a sense, it seems to have a negative learning rate. Why that is the case, long story, hours-long discussions, but it probably has to do with the fact, well, with two things. One, we keep making them more difficult to build because we want them to be safer and safer. And so each time, when we build a nuclear power plant today, we don't build it in the same way as we did in the 60s. So we build a way more complicated and safe structure that just costs additional billions. And another thing to keep in mind about nuclear energy is that it basically is the case that you don't build these things in a factory and build 1,000 identical nuclear factories one at a time. There isn't such a thing as a nuclear power plant factory. Each one that gets built is sort of a unique project that's just one of a kind, that's being totally engineered from scratch. And so that also makes things more expensive, where in comparison, solar panels, windmills, they get produced on a large scale. There are factories that just pump them out one after another, and that leads to cheaper prices, which you can't easily do with nuclear. Okay, let me take a quick look what time it is. Half an hour. Okay, I will then quickly say something about this machine, and after that, well, actually, electricity's role is also very short. So I'll take the two next points, and then we can take a small break already because the trading electrons part is going to take some fresher minds. So the machine. Think about all of the stuff that humanity has built since the start of the modern age. We've built a few amazing things, and you can ask yourself, what is the most amazing machine or most complicated big thing that we've built as humans since the 1900s or whatever you want to take as a starting point? Does anybody have any personal opinion on what you think is one of the most amazing things we built, or any ideas about what the most amazing thing is you think we ever built? And any opinions? I would actually be really interested to hear what you guys would think of. Go ahead. Space station, nice. My next slide is the space station. Okay, it's indeed, I agree. It's one of the most amazing things, right? It's this huge laboratory, incredibly complex. These are all solar panels floating around the Earth since many years. It takes 90 minutes for it to make one cycle across the Earth, and there's people in there that are there for several months on end, and so it's an incredible thing, the space station. Any more? Any other ideas about incredible things we built? No? My previous slide was another candidate, I would say, namely the Large Hadron Collider, which you may have heard about. It's partly in France, partly in Switzerland. There's a machine underground that's basically a long tube, and it's more than 20 kilometers long, and we use that thing to accelerate tiny particles, and physicists use those experimental those experiments to study the origin of the universe and the Higgs boson and all those things. You may have heard about it. It's another incredible machine, this particle accelerator. But what I want to, of course, come to, and what you may have guessed, is that I think that the most amazing machine that we have built so far as humans is our electricity system. Because it is, if you think about it, one huge machine. Every light bulb, all of these televisions, every power plug in this room is all connected with wires that are connected to other wires in the street, which are connected to bigger wires like those that you are familiar with when you drive on a highway or something, right? You see these pylons with the biggest wires, and all of those are connected to all different kinds of power plants, to windmills, to nuclear power plants, gas power plants, solar fields, and that entire network, which you can see as one big machine of producing electricity, and a lot of wires connected all over the place, all the way to every appliance that's plugged in somewhere. It's one huge thing that's sort of continually operating more or less perfectly, 24 hours a day, every second of the hour. And it's incredible. I mean, if you see what, these kind of pictures from, I believe it's New York, it's something that would have just seemed completely alien to someone from 100 years or more ago, right? What we can do with this incredible machine that we've built, this electricity system. You can even see the effects of the system, let's say, from space. Those astronauts on the International Space Station, they can see parts of this. All right, you can clearly see where in the world we use a lot of electricity in the form of, using electricity for lighting. Japan's very visible, India, right, the eastern part of China. And you can also see, in fact, where there aren't so many people living in the world, right? Most of South America and Africa and Siberia are basically empty of, empty in terms of large-scale electricity use. It's kind of beautiful, I think, to see this electricity system from this perspective. It's in a way a bit comparable to the veins in your body, right? Which is a similar kind of a network of big highways and then smaller streets, if you will, going to each part of your body. It's like that if you look at our society as well in terms of our electricity system. This is a picture, by the way, of Flanders, and you can see two cities in here. Anyone want to guess? Go ahead. Yeah, exactly. Right. And that must be Brussels, I guess, below. Another one you can see here, zoomed in on Europe. Flanders is pretty visible over here, right? Lots of economic activity in this part of Europe, lots of electricity on the highways, etc. And if you look at it in a more abstract way, which I do in my research and in the models that I make, in the simulations that I run for my papers, it's also sort of interesting to see, okay, this European network of interconnected electricity systems also has some interesting properties. So, for example, you can see that Germany is completely surrounded with other countries and therefore with other electricity systems. It's very well embedded, like a sort of an island in between a lot of other opportunities to exchange, to sell, to buy from countries around Germany. Whereas if you are, for example, Portugal, you are way more isolated and you'll have to In terms of electricity, you'll have to be more self-sufficient in a way, right? You can export or import a bit with Spain, but that's pretty much it. So each country has sort of its own little location in this international network. That just gave you an idea of how amazing. I hope I could convince you at least a little bit that this machine, the electricity system, is incredible, especially the European one actually, because we are across Europe very well integrated. So you have some electricity systems in individual countries elsewhere in the world, which are just an isolated thing. But the European case is extra amazing, if you will, because of the interconnectedness as well across all of those countries. Okay, enough about the machine. What is the role of electricity in the energy transition? So going back now to the energy transition that needs to happen, and we can ask ourselves, okay, we need to bring down our emissions to zero on a net basis globally. So that means that anything that emits at the moment needs to become carbon neutral. That's industry, that's buildings, transport, agriculture, electricity generation. All of these parts of our modern society need to become carbon neutral somehow in a very short time span as well. And so what is the role of electricity in that story? Well, some people go as far as to say, well, it's basically the answer to almost everything. And they say, to get the energy transition done, to make everything carbon neutral, we need to electrify everything. It's a slogan, right? Not an academic statement. But it's a good one to remember. Like, okay, electricity is really important. We're going to do much more with electricity than we have historically. You can think about all of the things that we do not use electricity for yet today, right? I mentioned them before. Heating your home. At the moment, you probably, if you're living in Flanders, burn gas, right? Burn gas to heat your home. If you drive your car, may not have a car, but if you drive a car, the car generally burns a fossil fuel, right? Diesel or gasoline. In industry, a lot of things still use coal, like producing steel to make cars, steel to make buildings and other things, right? Producing steel is still something that consumes a lot of fossil fuels, generally speaking. And so we know that a lot of that stuff, not necessarily all of it, could be taken over by electricity, so that we use electricity to do those same things instead of burning some fossil fuel. And that can be depicted in this figure, which you know is the only figure. After this, we can take a break. That I still want to explain to you, and I think it's really important to understand and to stand still a few minutes here. We see two parts: left part, right part. The part on the left is basically the world of today, and the part on the right is where we intend to go. By that I mean what sort of the consensus is, more or less, among energy experts of where we are, roughly speaking, going to go towards societally. But of course, there's always going to be discussions about where exactly, and the figure on the right may look a bit different if you listen to different experts. But okay, the figure gives you an idea, past and future, or present and future rather. What does the present look like? You have a big circular shape in red or salmon color. And that represents our total amount of energy use as a society today. So that means, you know, the sum of everything we use energy for, everything. And within that, you have a smaller blue part, which shows everything we use electricity for today, right? Which is, our electricity use is a significant part of our total energy use in society, but it's not, of course, the only thing, right? Again, we drive cars that don't use electricity. We heat our homes by burning gas. That's all energy use, but not yet electricity use. So electricity today is a small part of our overall energy use. And if we look inside the blue part on the left, you can also look, okay, within electricity, how much is coming from renewables and how much of that electricity is still coming from other sources. Now what happens when we jump to the right, to the future picture, we see that the total salmon color area decreases in size, which means we are going to use less energy. In terms of total energy use, we are going to become more energy efficient, right? At the same time, the amount of electricity we use, which is in the present only a small part of our total energy use, will increase a lot. So while we use less energy, globally speaking, we will use more electricity. Because electricity will represent a much bigger part of our total energy use. That's called electrification. We're going to electrify a lot of things that we don't use electricity for yet. And then if you look inside of the electricity figure, of course, what is being depicted is that the ways of producing electricity will at the same time also change towards being based to a larger degree on renewable energy. So it's a really important picture to keep in the back of your mind. We're going to, globally speaking, also in Belgium, in Europe in general, we will decrease our total energy use, but we will increase our electricity use because electricity will be a bigger part of overall energy. And if you zoom into some concrete examples like cars, today a fossil-fueled car is very energy inefficient. It basically throws away 2 units of energy for every 1 unit that is actually used to move you, right? So a car primarily produces a lot of heat that is just emitted and lost, and it also, for about 1/3, actually moves you around. So it's just a fossil-fueled car engine is just a really, really inefficient thing. You have a lot of energy that's actually in the fuel. It goes through the engine. It's converted to wheels turning, but only 1/3 of the energy actually goes to turning wheels, and 2/3 actually is thrown sort of away in the form of heat that's being generated by the engine. And so what that means is when you go from a fossil-fueled car to an electric car, you will use way less energy because you stop doing that wasteful thing of throwing away all of that heat energy in your combustion engine of your regular car. That stops all of that energy waste, and instead you move yourself around in a car that uses energy way more efficiently. An electric car only throws away about 5% of the energy that's in the battery. You know, almost all of it goes to actually turning the wheels, so to speak. An electric motor is way more efficient. Go ahead. Right. So in the long term, we will perform this energy transition globally, and so this is a global story in that sense. Although I did come to think of it, make one mistake in what I said earlier, which is that the reduction in overall energy use, it is happening in Belgium and in Europe overall, but not yet globally, right? So globally, the total energy use is rising, right? Because China, India, and many other places like that are each year using more energy than the year before, right? So although they, to some degree, have opportunities to skip stuff that we did, right? So for example, in China, and especially in India, for example, before they would ever reach a situation where, well, a majority of households have a private car, as it is in the West, they won't go through the phase of every household having a fossil fueled car, right? They'll just sort of skip that and go to electric vehicles. Although, again, it's obviously not desirable that 8 billion people each have their private electric car. So it's a totally different story to drive car ownership down. But again, we're not going to drive that down to zero. Please, go ahead. Right. Mm-hmm. Mm-hmm. Hmm. Right. Okay. Okay. I very much enjoy that you are aware of this, and it's not in my slides, and perhaps it should be. So you can indeed look at. So it is absolutely true that geographically speaking, the emissions in that area of the world are increasing. That is itself, of course, not a lie. It's also true that if you look at per capita emissions, so in each country, the total amount of emissions divided by the amount of people in that country, China is still way lower than any European country or the US. And of course, other countries are much lower than China still. So per capita, per person emissions are by far the highest in the Western part of the world. The number one spot is actually Qatar, not a Western country, but that's a sort of an exceptional case. And there's an important story about production compared to consumption perspective on emissions. Absolutely true. However, it is the case, fortunately, that you can calculate, and this has been done. How have consumption-based emissions evolved over the previous 20 years in Europe, for example, also in the US? So that means not just looking at how much is being emitted within European countries, but also how much emissions are actually embodied in all of the stuff that we import from other countries, other parts of the world, stuff that we import from China that was produced there, and then probably that emitted something by way of producing it. If you look at consumption-based emissions that take imports into account, luckily those have also been decreasing. And so you can just look at all of the best data available on that. You can surf to Our World in Data, and you will see that this is the case. But I'd be interested. Please go ahead. By the way, I'm not saying it's fine. They are the bad guys. We are the good guys. We are doing okay. It's they that have to change. I'm not saying any of those things. So I want to make sure that I confirm that, just to make sure that you don't feel like that's what I'm saying. But please go ahead. Okay. Right. Yeah. Yeah. It is possible. I'm not specifically informed about the Finnish case. And I know this discussion is, for example, also ongoing in Norway, where they produce most of their electricity with hydropower and they feel super green. But in fact, the Norwegian lifestyle, which is sort of on the high end of European lifestyles, relies on a lot of emissions that take place elsewhere. And so it's absolutely a valid discussion to have. We can take a look in the break at the data, which I do know how to find in a minute for Finland. I'd be interested actually. Finland has a very green electricity mix, generally speaking, in the sense of not emitting a lot of CO2. But absolutely, so we do need to take into account the emissions that we are sort of responsible for that take place outside of our own country, and it's absolutely a valid point. Go ahead. Yeah. So it's still a huge, indeed, it's a huge difference, right? So we are decreasing year over year. They are increasing year over year, but they are nowhere near our levels at the moment. So we do need to worry about India in that sense. We do not want them to go to 15 tons. We want us to go to 5 and them to also not ever exceed 5 while gaining a similar standard of living as we do. So all of that is absolutely true. And actually, thank you for the reminder that this is important to keep in mind as well. And so I'll include it going forward into these slides. That brings me to the last, and I think this is a slightly bigger part about how do electricity markets work. It's the closest thing to what I do research about, real energy economics. And before we start that, I think you can use a break. So let's maybe reconvene in 15 minutes, if that's okay. Yeah, all right. 15 minutes. See you. Feel free to come to me if you want to discuss further. Let me restart my recording. Okay. So we trade a lot of stuff. The economy is full of it, right? When we go to the bakery, we exchange bread for some money or whatever. A lot of trading going on in a modern society. And in particular, the way we trade electricity is interesting and extraordinary. So I would like to give you a bit of a crash course on that topic. It is an incredibly complicated topic if you really dive into it deeply. It's a kind of a rabbit hole, and I feel confident in saying that a very, very small amount of people, excluding myself, by the way, understand the electricity markets in every detail, right? It's just so immensely complicated. But what I intend to do today is to give you, like I said, a crash course, a general helicopter view, so you just have a general understanding of it. So basically, what we're interested in is avoiding this. It's difficult to see from the back, I imagine, but does anybody see what this depicts? Which it's a city in the dark. It's an actual picture, a real picture, not photoshopped or anything, of a skyline. Do you guys in the front maybe recognize which city it is? Any guesses? Go ahead. Yeah, exactly. It's indeed a power outage in New York. This is the what's it called? Forgot its name. The Rockefeller Center and the Empire State Building. And so this happens every once in a while, that the electricity system sort of crashes, and we would like to avoid that as much as possible, of course. We like to have electricity available simply always, 24/7, and we sort of don't think about it, right? When we turn on the light, it's just always there, always available, no matter which time of day or whatever. And so the question of how do we avoid disruptions in our electricity supply, we do it with markets today in Europe and many other parts of the world. And more specifically, we do it with forward markets. So that means markets where buyers and sellers agree on an exchange and arrange contractually who's going to pay what, etc., before the actual delivery of the good. So a forward market for bread would be, arranging with your baker that he's going to make a bread in 2 weeks for you, and then maybe you already pay in advance. It's like a forward market, right? And so for electricity, we use a complicated web of different forward markets to make it all work. But before I delve into how it works today, it's it's good to have some idea of where we came from, how it used to be before we did it with markets in Europe. And how that worked was basically we had, before the 1990s, all across Europe, monopolies, mostly state-run monopolies. Belgium was actually an exception in that case, where we did have a similar monopoly as in other countries, but it was a purely private one. It was just a private company doing everything that had to do with electricity. In other countries, it was basically the state-run company. And so what that meant was one single organization was responsible for generating electricity, producing electricity, transporting it, first along the large cables, the thick cables, right, the core network, and then also across the smaller cables that are in the streets everywhere in order to do the last part until it reaches your home. All of it done by that company. Also the system operation, which means, okay, you produce electricity now, okay, stop producing, now this windmill is producing, okay, please increase your electricity production a little bit. Basically being like the guy above it all or the girl above it all, and sort of operating the system, making sure that everybody plays nicely and that it all comes together in a way that just gives available electricity at all times. System operation, also done by the same company back then. And then also billing. So the whole process of having some kind of a contact with each and every user, each and every individual household that receives by mail, or today by email it would be, but okay, back then by mail, you know, a letter giving you your personal bill of this is how much you used and this is how much you're now expected to pay, and then checking whether or not the payment was made, and if they don't, then maybe recontacting the household. Billing, it's also a very big part of running an electricity system, and it was also done by the same company. So that was the world before the 1990s in Europe, one company doing everything, and then in the 90s, a process of liberalization began in Europe, where so we in a stepwise way gave more and more responsibility to markets. That's more or less how it was. Yeah, it's a little bit roughly sketched. There are some nuances to be made, but generally speaking, that's how it was. So each country having one. So some big countries maybe had two. I mean, in you know, during the Cold War, obviously in Germany you had different parts, you know, with the different companies. But so also in other countries, due to some historical reasons, maybe it was two or three, but generally it was one. And that's the sort of the easiest way to remember roughly how it was. And so we started having the idea in the 90s that, you know, the quality of service that we got from this one big, often state-run company could be improved. Maybe the way they operated could be improved in order to reduce prices if they somehow became a bit more efficient in terms of, you know, yeah, running the company, doing the operation and maintenance of all the machines and the grid and all of the employees involved in that. We you know, in the 90s there was a wave of thinking about let's give markets more responsibility to arrange this, and that will be to the benefit of end consumers. All of these households who have to in the end pay for the electricity, they'll get a better service and maybe also a better price if we let it be done by markets instead. And so the way we did it is that we went to a split of the different activities that have to do with generating electricity. We said, okay, there are still a couple of things that are most logical not to leave to markets. We call them natural monopolies. You could literally say it's natural to remain it as a monopoly. And what are those? Those are basically operating the electricity grid. Imagine if we had 10 different companies all building grids and competing with each other. We would have 10 times as many electricity grid. You know, everyone, you know, asking you, come to my grid and connect to my cable. It will be cheaper. That would be incredibly inefficient. So it makes a lot of sense. It's a natural monopoly to have just one company that is the owner and the operator of the grid itself, so the cables themselves, to do the transport of the electricity. Although, one nuance, we did split it into two different activities. One organization managing the big cables that you see in the air, you know, and the big pylons. That's called the transmission network. They are like the highways of electricity. One company builds those, invests in those, manages them, operates them. And then another company is responsible for all of the smaller cables in the street. And so those are, you know, millions of kilometers. In every street there are cables like that connecting to each individual building. And so that's also a separate activity. That's called the distribution grid, right? So transmission grid, distribution grid. Two different companies are still in a singular way responsible for those. But when we liberalized, we split off something which we then called competitive activities. Things, you know, certain parts of the electricity system that we thought those can be done by companies competing, and that will be, you know, good for the consumer if you have many companies each trying to do their own thing. And those are basically generators and retailers. Generators generate electricity. So somebody, as a company, builds some windmills, and that's his investment. He buys a windmill, installs it, and then wants to sell the electricity. It's just a generator. That could be a company. Also, somebody building a gas power plant, a generator. And you can imagine many of them, each, you know, in the landscape, doing their own business and investing in their own electricity production capacities and competing amongst each other to sell the electricity that that these installations produce. Generators, that's one competitive activity. Then you have the second one, retailers. Those are companies that do not generate electricity, but that buy electricity from the generators. But those are, of course, very large volumes of electricity. You know, out of one windmill even comes enough electricity for many, many households. So a retailer is a company that buys those large volumes from generators and basically splits it up and then sells it to each of us. All of these, you know, millions of small individual end consumers. That's a separate competitive activity, being a retailer, like the middleman between the generators and the small end consumers. You can also have competition there. You can have 10 different companies who say, you know, my activity is going to be to buy electricity in large volumes and to split it up and to sell it to end consumers. And so retailers is basically the company that you think of as an energy company when you have a contract for electricity or a contract for gas at home. In Belgium, you may have a contract with a company called Engie or Eneco or EcoPower or Mega or Luminus. These are retailer companies. And so they compete as well. They try to do the best job of like, oh, I will make sure that, you know, if I send a bill to people, that it's a really nice, clear bill. And that's why people want to come to my company to get a contract for electricity. Or, you know, when you go to the website, you have a very nice interface where you can see information about your household, how much you are consuming and everything. You know, retailers try to compete with each other to attract people to them, and so their activities they try to be competitive at. Please. Yeah. Right. Yeah. Of course. So it's a bit complicated, but indeed, so primarily, in fact, it's prices that they compete on, and not necessarily the way they design their bill, as I just said. But indeed, as you allude to, they all buy electricity from the same market of generators who generate electricity, and so they all sort of buy electricity on similar prices, and they can't. I mean, the way they can offer a somewhat lower price to you as an end consumer would mainly be by being as efficient as possible and basically being as small as possible, not having too many people working for you as a company to do all of this billing and all of the, you know, this management of being the middleman. If you do it as efficiently as possible, you can take a smaller margin on top of what you pay for the electricity generation, and therefore then offer a lower price to the end consumer. So those are retailers. Please.
How useful are retailers when you think about it? Like, why can't we just go straight
Yeah.
to the generator? Because there's often, the saying of like, oh, you have to cut out the middleman because it makes the end product more expensive.
Right.
Was there a concrete reason that we can't go straight to the generator because it's too much work for them? Or?
No. So, well, the main reason is that they just produce way too large volumes. So it's that's sort of the difficult thing, and also, that's actually what a lot of my coming slides will be about. In the market where generators sell electricity, the electricity price is different in every hour of the day. And I'll come back to that, and I'll explain that. But one of the ways that retailers are a thing is that as a middleman, they can say, okay, I'm going to be exposed to this continual changing of electricity prices every hour on the wholesale electricity market with the big volumes. And I will package it into something I can offer to an end consumer of like, you get a fixed price for 1 year. But in fact, this price isn't fixed, and the generators have hourly prices, and it's because of the middleman, the retailer, that you can have as an end consumer this package of a fixed price, for example. And I'll come back to it, but actually it's becoming possible. So since I think the 1st of January last year, it's now obliged from the European level in all member states that it is possible for a consumer to take what is called a dynamic contract, which means that you pay also for your electricity with varying prices every hour, directly connected to the world of the generators, basically. But of course, that exposes you to some risks. Like maybe you will be using a lot of electricity and turning on your washing machine in the hour when electricity is very expensive, and then you have to think about that, and maybe you get a big electricity bill because of this risk exposure. So it's a complicated matter. So not everybody wants to do that, but it's becoming possible. Yes. Right. So in principle, everyone is free to build a nuclear plant, coal plant, gas plant, windmill, or whatever. One of the ways in which it is being steered, in a sense, what is going to, from what are we going to get more of, and what is probably going to decrease in size over time. That sort of steering that the state does happens in a variety of ways, but the most important way in Europe is the fact that we basically have a price on the emissions. So today, if private investors decide, I'm going to build a new coal plant in Belgium, it's allowed to do that, but it's just that you're going to pay so much now for the emissions that it's just very economically unattractive to do. Then how does the state make sure that there's enough electricity being generated? Also a very complicated story. Could give 3 classes about that, but it's one of the ways it works out is that if we are tending towards not having enough generation capacity to meet electricity demand at all times, then electricity prices are going to rise. And that will trigger investors to feel like, whoo, I'm going to invest in some new electricity production capacity because you can get nice prices. And when a lot of them do that, we again get overcapacity, and then prices are depressed again, become lower again, and it's not attractive to invest in new generators for a while. And so this is sort of one of the ways in which it works out. But trusting in that 100% is sort of hard for states to just leave security of supply to the market. So there's a variety of ways in which the state tries to supplement the market activity to really make sure we always have enough electricity. But I can't go into those in detail, unfortunately. Please. Right. Yeah, exactly. You're paying attention. So in a strict legal sense, you have separate companies, Engie the generator and Engie the retailer. Same with Luminous and other companies that used to be, back in the day, companies that had both production capacity and also, you know, were kind of a retailer, and that was split up, legally split up. And so you now have to have these separated. So Engie, for example, split up into generator Engie and retailer Engie. But of course, generator Engie sells to retailer Engie at maybe a better price than would otherwise be the case amongst you know, really different companies, because of course they're still, those two companies are still in the same building, and you know, it's basically the same management. So so yeah, but it's interesting. So you also have companies that are only retailers. So for example, in Belgium you have Mega, which is yeah, it's just a retailer. You can go there as a private person, get a contract for electricity, but Mega does not have any production means of generating electricity. So they purely have to go buy big volumes of electricity from generators to meet their customers' needs. You also have generators that are only a company that has a gas plant and sells it as a generator, but doesn't have any contact with households that buy the electricity, because they just sell to a retailer, to a middleman who does that job. So you have every possible combination is existing out there. The idea is that they are both competitive activities that you want sort of as a separate arena, with competition being, you know, companies fighting it out between each other in order to get the best possible service and price out of that competition. And sort of retailing is sort of seen as a separate activity that's useful to have a competitive arena for, and generating is its own. But what you suggest of, like, wouldn't it be better to just sort of have them cooperating a bit, and you know, that actually happens in practice. So Engie the generator and Engie the retailer heavily cooperate in the sense that, you know, it's yeah, basically transactions between them make it such that it basically almost is equal to if it would be one company, one big company, Engie. It's just that legally speaking, it has to be two companies. But in practice, generator and retailer Engie basically operate as if it's one company. But it's just good to have it split, because you have the possibility for someone to start a company that's just a generation company, and that's just going to compete in the world of generating electricity. And you have the possibility of someone entrepreneurial to start a new retail company, and he's not interested in having you know, a plant that operates electricity, that generates electricity, just wants to be really good at being a retailer. So he's going to buy electricity in big volumes and sell it to end consumers. That's why you have the arenas. Please go ahead. Yeah. Yeah, exactly. So you have cooperative companies where you also, yeah, you have a lot of windmills, usually in the Belgian case, and they sell to their own customers who are also the owners of the company. So they own the shares. So that's why it's a cooperative, EcoPower. But indeed, so and on paper, legally speaking, you have the generator EcoPower and the retailer EcoPower. It's just that the retailer EcoPower only buys from the generator EcoPower and only sells to its own customers. That might not be the case in other retailers' case. Okay, so that gave you, in a bit of a prolonged way, a view on the past and how we went from monopoly situations to a split of different activities, and now, you know, a competitive arena. And so I want to come back now to this world of forward markets, right? The markets that we use to avoid blackouts, to arrange the trading of electricity. And this is the slide I showed to some other students that sort of, you know, I can spend an hour on this slide because it gives the entire picture, more or less, of the different market structures that are all operating as one big sort of machine as well. But I'm not going to go into all of those today. That would take me too far. So I'm just going to explain what I think are the two most important parts, which is what you can call the long-term market and the short-term market. Strictly speaking, called futures markets and the day-ahead market for electricity, remember. So let me try to explain those two. I like to use the analogy of selling or buying bread. Imagine that you are the, the father or the mother at the head of a household with 3 children, and okay, we're a family of 5, and I'm just going to say something. We eat 2 breads a day, and you're trying to manage, for this family the supply of bread. For the long term, you want to make sure that you always have enough bread, that you're never sort of left without bread. Think of electricity. You want to make sure you always have enough of it. And so what would you do? The way it works efficiently is that you have both a long and a short-term market for bread, which doesn't really exist for bread, but just for the analogy's sake, imagine that this father or mother can go to the market for bread, the long-term market for bread, and say, well, I'm planning for next year, 2024. I know that on average my family eats 2 breads a day. So let me please, I want to arrange with some bakers of bread to already sign contractually that I will buy every day 2 breads from that person. And so that producer, baker, would also, have some interest maybe in having already the certainty today that all of 2024, every day 2 breads being sold to that, father or mother at this pre-arranged price. So today we agree, the father or mother and the baker, 2 breads a day for all of 2024, every day, for a certain price. That would be, by analogy, the long-term market for bread, but now just imagine for electricity, right? So you can buy electricity, fixed amounts for every day from somebody that can offer to you to produce amounts of electricity every day for all of next year at a certain price, right? And if you are a retailer, which I explained before, right? You are like the mother or father. You know that you have a family of customers that are going to consume a certain amount of electricity, right? And for next year, you already want to make sure you buy enough to, broadly speaking, cover the needs of your family, of your consumers, for all of next year. So as a retailer, you try to buy on the futures market big volumes of electricity fixed for every day, and that already more or less covers your needs for all of next year. That's the forward market. Of course, there's uncertainty in how much bread your family is going to eat every day, right? It's not going to be exactly 2 breads every day. And that's why there is a need to also have a shorter market. 2024 occurs, and then from, along the days of 2024, once it happens, you already pre-bought your long-term contracts, 2 breads a day, right? You already have this supply for your family, for your customers as a retailer. But then there's a day where you go for a weekend with your family on a holiday, and you're not at home for a few days. And on those days, actually, you won't be buying any bread. You're somewhere else, maybe buying paninis or whatever. And so you already pre-contracted your 2 breads a day in the long-term market. So now you want to sell this excess bread that you have for these few days, right? And so you can do that on the short-term market. You can go there, and it's kind of a, one day in advance. Oh, tomorrow I have, a couple of breads excess. I bought them on the long-term market, but I don't really need them now that the day arrived, and I saw that actually we're going to be on holiday. And so on the short-term market, you can sell that to someone interested. Oh yeah, actually I have a shortage for tomorrow, so I want to buy some extra breads that interests me. So conversely, there may be a time in your family when there's a big gathering of uncles and aunties or whatever, and maybe that day you need 10 breads or whatever. Can go to the short-term market. You only have your pre-contracted 2 breads a day, so you can go buy some extra breads on the short-term market. short and long-term markets, they exist for electricity. And I gave in my example always, for 1 year, I said the year 2024. But in fact, what you have, and that's why it says futures markets, plural, you can today, as a retailer, buy a large volume of electricity for next month, for next quarter, for the month of November of this year, for the second half of 3 years from now. Those all exist. And so you have an entire space of producers who can sell for these different future timeframes, and buyers who are interested in buying those kind of fixed products for future timeframes. Futures markets, and then the day-ahead market, that's just one, the short-term market for electricity. Okay, I hope that made somewhat clear what the short and long-term markets for electricity consist of and why they're useful. So now I will take you to a brief recap of what happened last year before I continue talking about the way the electricity market works. Because first, we need to have some background, okay, the story of 2022, basically. I'm obviously not going to give a full overview of last year, but just want to focus on what happened with gas. And I imagine you already were exposed to some of this in other classes, but as you know, Europe has, had a very strong dependence for natural gas on Russia, which supplied, before the war in Ukraine, about, well, it fluctuates from year to year, but about 40% of the gas consumed in Europe as a whole came from Russia through these pipelines, which you see depicted here in a nice big fat line. As you can see, you have some pipelines going from Russia straight to Germany, called the Nord Stream pipelines 1 and 2. And then some going through Belarus and Poland, and very important ones going through Ukraine itself, which put Ukraine, who wasn't best friends with Russia, in a very strong position, because they, Russia was to some extent dependent on remaining, friendly with Ukraine, because, Ukraine had on their territory these big pipelines to transport the Russian gas and allow Russia to sell to Europe and make money from that. So that's why over the years Nord Stream was built. First Nord Stream 1 and then quite recently Nord Stream 2 for Russia, in order to be able to circumvent Ukraine, in order to be less reliant on those pipelines. And okay, the rest is history. So the war in Ukraine broke out. Nord Stream 1 and 2 are now basically dead. You may notice they were even sabotaged, presumably by the Russians themselves. So those pipelines are damaged, and it's unclear at the moment whether they are ever going to be operational again. And due to the war, the amount of gas flowing from Russia to Europe has sharply declined, as you can see in the top left there, which depicts the flows through all of these pipes from the start of the war until late last year. Today, we still some gas is flowing, but it's basically minuscule compared to what it was. And yeah, what are we planning to do in the short term to get an alternative supply of gas? Because it's very hard from 1 year to the next to just completely not use gas anymore. That's not necessarily feasible. So before we move away from gas, from using gas or so much gas in the long term, in the short term, what Europe basically does is try to import more gas instead of from Russia, from other places around the world, not through pipelines, because it's very hard to build a pipeline to the US, for example, through the ocean. It's not feasible. So instead, through shipping. So shipping gas around the world, which is called LNG, liquefied gas. And the orange dots here on the map show you where in Europe we have places where the gas coming from ships can actually, connect to the mainland grid and insert the gas into the European network. In orange, the ones that we already had before the war, and in pink, the ones that we are now in a hurry trying to add to the European coastline. Yeah, And this has resulted, as you can see here, the yellow shows the evolution of how much of our gas came from Russia along 2020, 2021, and then 2022. So in the final third of the figure, you see that the yellow part becomes very small. European supply from Russia becomes very small. And what becomes very large is a new supply in LNG form, which mostly comes from the United States. But this is more expensive. It's not as cheap to put gas under high pressure onto a boat and then carry it over here and then, you know, change the pressure from high to low again, get it into the grid. That's a more expensive endeavor than just putting gas through pipes. So gas is probably going to remain more expensive. But what happened actually last year with gas prices is this. So for the longest time in Europe, more than 10 years, gas prices were very low, about 30, 40, 20 euros per megawatt hour. That's an expression of a gas price. And then so that's this period, right? And when we started getting these satellite images late 2021 of the military buildup at the border between Russia and Ukraine, the gas price started increasing, and when the military conflict actually initiated with Russian tanks entering the Ukrainian territory, the gas price basically exploded because there was a huge expectation immediately that almost half of the gas that we rely on coming from Russia would just go away, and there would be a huge scarcity of gas. A lot of willing consumers that want to consume gas, but not as much gas available. So a lot of bidding wars basically happening, and then what you get is much higher prices. Now, luckily after that, due to the fact that we were quickly successful, to some degree unexpected, to ramp up our alternative supply of gas from, amongst others, the United States, using these ships. Also, we reduced our gas usage by a lot, including by shutting down factories temporarily, etc., and by maybe turning our thermostats a little lower. And all of this in unison resulted in the gas price coming down to earth again in recent months. What this did to the household bills for gas, for heating your home, is depicted in this figure. What you basically only need to see, and it's okay all the way from the back, is that it used to be every year almost the same, the gas bill for heating your home in Flanders or Belgium probably in general. Per year, a sort of average amount you pay for gas is about 1,000 euros. So less than 100 euros per month. And this exploded to about 3,000 euros per year. At some point reached way higher prices, but nobody actually paid 8,000 euros for a year. This was only what would be the amount you pay if gas prices would have been stable at this level for a full 12 months, which didn't happen. But anyway, today still gas bills for households are about 3 times as high as they were before the war in Ukraine. So about 3,000 euros per year instead of 1,000. And this is what now the important part. The electricity price totally followed this. Sorry, go ahead. So it's not a black and white answer. So a lot of people, a majority of households in Flanders, when the war in Ukraine started, had, and this was always the case for many years, contracts for buying electricity and gas that had a fixed amount, that had for a fixed amount of time a certain price, a fixed price for 1 year, for 2 years, for 3 years. So if you were very lucky, in a sense, to have started a new 3-year contract for your electricity and gas, which had a fixed price just before the war started, then then this is the price you pay for those full 3 years. And then after the contract ends, you have to go to the marketplace again and get a new contract, and then we'll see what the price is. But not everybody had that. So a lot of people had 1-year contracts, which then ended sometime late 2022. And so all of them had to go ahead and go get a new contract, and then the prices of new contracts for, again, 1 year or something were much higher by then. So if you had a previously active contract from before the war as a household, you would not be exposed, but not everybody had such a contract. So some people have a contract with a variable price, which automatically follows the evolution of the price on the market from month to month. And if you have that kind of a contract, you just felt, every month the evolution of this price. Oh, I'm sorry. Right. Reserve. Yeah. Yeah. Okay. So, it is indeed to some degree the case that it's so a variety of things are true for a variety of households and each their own situation. So it's not a black and white thing. So like it's bad for everyone or good for everyone. What happens next winter is entirely dependent on a lot of things that are still uncertain. So it might be an extremely cold winter next winter. It might be the case that China, who is currently suffering heavily from COVID, succeeds in dealing with it. And if the Chinese economy reactivates, they will have a much higher demand for gas again. They will compete much harder again with Europe, and that will also drive prices up. So, and then there's a couple of other things like that. So if it's a much colder winter, if China regains its economic activity as before, and some other things, if all the stars align in a very bad way, then next winter could be horrible. If all the stars align in a good way, and so this is very uncertain to a certain degree, it could again be quite okay. So it's a very complex story that is uncertain to a certain degree. But what I wanted to emphasize here is that the electricity price followed the gas price. And you can think about why is that? Because we don't import our electricity from Russia, right? It's just the gas that we get from Russia to heat our homes or run our industry. But why does the electricity price also increase that much? Why does it, in fact, almost perfectly follow the gas price evolution? Well, okay, we know that in some countries, and not even everywhere in Europe, we have a certain amount of our electricity being generated using gas, but certainly not all of it. We have a lot of wind and sun and nuclear power plants, etc., coal plants. So why would the electricity price perfectly follow the gas price? That's sort of what I want you to ask yourself, what I'm going to try to explain. Yeah. Also, the bills people pay for electricity similarly increased. So, okay, some questions, as I was already alluding to, that I want you to ask yourself are, okay, why do I hear all the time in the news that electricity prices are coupled to gas prices? This is something you may have read at some point throughout last year. You may also ask yourself, why is the electricity price determined? That's also something you read about, that the electricity price is determined by whichever is the most expensive producer of electricity that we use at a certain point. So if we produce some electricity with wind and some with nuclear, some with coal, but in order to meet the total demand for electricity, we then also use some gas. This results in the electricity price for everyone being set by gas. And so, however expensive it is to produce electricity with gas would determine the full electricity price. That's something you read about. And so you can ask yourself, why is it? Why is that the case? Also, as I talked about before, electricity prices, they continually fluctuate every day on the wholesale market, so the big volumes where the retailers buy and the generators sell. In that market, the electricity price changes from hour to hour every day. And that's a funny thing. That doesn't happen with other products. You know, coffee or beer or grains or you know, whatever, oil. You know, they don't have these sharp price fluctuations every hour of the day. But it is the case for electricity, so we want to understand why that is. And then, as I already sort of gave the answer to this because the question was asked, why don't I notice that in my electricity bill, that the price of electricity changes from hour to hour? Quick. So, as the energy crisis unfolded last year, there was a lot of pressure on governments in the EU to think about, you know, the whole way it was set up, the electricity market. They call that the market design, the way the markets were designed. Governments had to sort of take another look at that, and a lot of voices started, you know, boiling up and saying, well, we should totally rethink this, and it's not functioning well because look at these huge prices. This cannot be a good system. We have to throw it away. And at some point, this reached the highest levels possible in European politics, where Ursula von der Leyen, in her State of the Union, in fact said that yeah, the electricity market is no longer fit for purpose. And these prices, they're skyrocketing. You know, we need a structural reform of the electricity market, and we need a new market model. These are all things that she mentioned in her speech. And so let's think about that, the market design for electricity, and do we need to change it? First off, some quick economics 101. Supply and demand. In any market, could be for coffee or beer or whatever, again, right? You have buyers and sellers, and the supply curve is upwards sloping, meaning that if the sellers receive a higher price, they will be willing to sell a higher amount, a higher quantity, right? Reversed, the demand curve is downward sloping. People, whatever, take coffee, as the price drops, the amount of coffee, the quantity that you may want to buy increases. And at a certain point, these two lines intersect, and the amount being produced is equal to the amount being consumed. And that's what we call the equilibrium quantity and the clearing price. So it's the balance between demand and supply that determines both the quantity of something being sold and the price at which it is being sold. Imagine what would happen if the price was higher than this point. If the price was higher, you would basically have much more willingness to produce. A much larger amount of coffee would be, you know, producers would be willing to sell and produce a much higher amount than is being demanded at that price. So there would be an oversupply. There would basically be coffee lying around because that nobody wants to buy, because at that price, sellers want to produce much more than buyers want to buy. If in the opposite situation, if you imagine what would happen if the price of coffee or anything is lower than this equilibrium, you know, then there would be not enough, well, there would be less willingness of sellers to produce, well, producers to produce that good, and there would be too much demand for that good. So there would basically be a shortage of coffee, right? Not enough being produced, too many being asked at that price. So whatever. So the clearing price is where you end up in a sort of a free arena of buyers and sellers when they meet each other. You know, imagine two large groups of 100 people meeting in a big town square, buyers and sellers of coffee. You let them do their thing, and what ends up is that, you know, a certain quantity and it will be sold at a certain price. Okay. Imagine now what that looks like, you know, for an actual product in a simplified example. So for example, if you have the market for grains, which are used to make bread or whatever, imagine that you have two farms, a modern farm and a traditional farm. They both together, they are the total, producers of grains, let's say. And imagine that the modern farm can produce 500 units of grains, and it can do so at a price of €2 per ton. And then another farm, which may use different techniques, maybe a lot of labor is involved to make the same grain, the exact same grain with the same quality as such, but they can produce 300 tons at a price of €10 per ton. Yeah. If you then have this downwards sloping demand curve that I just talked about, what you would see in this example is that in order to meet the total demand for grain, how much grain are people wanting to buy, you would need both the modern farm and part of what the traditional farm can produce. And the price at which grain would be sold, all grain, would be €10 per ton. And you can, of course, then ask yourself, like, is this fair? Because the modern farm also receives the price of €10 per ton, even though it only costs €2 to produce. And the way that works out is, if you basically imagine that the modern farm would sell at 2, what would happen? At a price of 2, there is a much bigger demand for grain, much more willingness to buy grain at a price of 2. So all of these people, consumers, they go to the modern farm and they all say, we all want your grain of price 2. And then what ends up happening, if you really imagine how this would play out in a real, town square, what would happen is some of those people would say, hey, modern farm, I would actually be willing to give you 3 for your grain, and others say, well, okay, I'm going to give you 4. And then some of these people standing in the group of the consumers on the town square, they may think, well, actually I'll buy rice instead, or I'll just buy some less grain. And they leave the town square, and so demand becomes lower as the prices increase. And where this sort of game naturally ends up, again, if you let them do their thing, is that eventually when they are bidding and the price reaches 10, then they become indifferent about, well, okay, I might as well buy for a price of 10 for the traditional farm, or the modern farm, don't care. And so that's where the price ends up. And this is then the equilibrium quantity and the equilibrium price. So in a natural environment where you let them do their thing on the town square, the producers and the consumers, where they end up is a price of 10 due to the bidding behavior that occurs. Another simplified example, which I'll spend way less time on because you now understand the general dynamic, is the market for oil. Very, very simplified way of representing it, but just to make a point, you have a global market for oil, but not every producer of oil can produce at the same price. Saudi Arabia, the oil basically comes shooting out of the ground, costs almost nothing to produce it, right? Very cheap to produce oil in Saudi Arabia. It's a bit more expensive in Russia and even more expensive in the United States. And if you then categorize sort of separately specific other ways of producing oil in various places around the world, shale oil is even more expensive and deep sea oil is even more expensive to produce. If you then at a certain point in time globally have a certain demand for oil, and it turns out that to meet that demand for oil, you need all the oil from Saudi Arabia and from Russia, United States, and part of the oil from shale oil. The price of oil will be equal to the production cost of the shale oil, even though all of those other guys are producing way cheaper. That's how it works out in a free global economy for oil. The oil price is set by whichever is the most expensive way of producing oil that is still needed to meet demand. So the price is not set at deep sea oil level because that's just not needed to meet demand, right? But it's set at this level. you now have a basic understanding of how this works in these simplified examples of the grain market and the oil market. And now I can come back to the electricity market, right? But seeing as I have progressed a little bit longer than I thought, let's first do a quick 5-minute break to at least catch our breath a little bit, and then we'll continue about the electricity market, okay? So see you in 5 minutes. Just a sec. And you might already be thinking the way in which we produce electricity will also be different from hour to hour. So it won't be exactly the same combination of technologies being used in every hour. And that, of course, well, depends on a variety of things. One of the things it depends on is, for example, how hard is the wind blowing, and how hard is the sun shining. If you have a certain demand for electricity in Belgium during lunchtime, and there is a lot of sun, then during that particular hour, the electricity demand in Belgium might be met with a large share of solar electricity. But then in the nighttime, zero sun, zero electricity coming from solar panels, the mix of electricity technologies that are being used to meet the demand in our country may look totally different. And at that time, you know, maybe if the wind is blowing, it may be a lot of wind. If the wind is not blowing, it may be more fossil and nuclear generation. So that mix fluctuates from hour to hour as well. If we now take the mix of electricity being produced for one individual hour, and now we use some fancy PowerPoint animations to put that on its side. The way we can basically look at this again, the short-term supply of electricity on an individual hour of the day, so that's why there's a clock and it says 6 to 7 p.m. in the evening, just as an example. For a particular hour of the day, you have a certain supply of electricity from different technologies. And this kind of looks like the traditional farm and the modern farm, or the different oil-producing countries, which each have their own cost of producing oil or grain. And so you have different producers of electricity, and they each have their own production cost to produce electricity, and you can rank them from cheap to expensive. And typically what that looks like is something like this. It's a simplified representation. You can have maybe one green technology all the way on the left. It can produce a certain amount, certain quantity, and at a certain price. And then nuclear, the same quantity, price. Another green technology, quantity, price. And you have maybe, this isn't the case in Belgium anymore, but some coal power plants which can produce a certain quantity at a certain price, which is increasingly higher. And especially last year, when gas prices were high, you know, power plants to produce electricity by burning gas would be all the way on the right. They can produce a certain amount of electricity if you want to, if that is asked from them, for a certain price, you know, and maybe a cheap and a more expensive gas power plant. Why would the price be different for two gas power plants? Because not every gas power plant has the same, you know, one may be much older and it may need to burn more gas to make the same electricity than the modern gas power plants. And so there's price differences, even in one technology. So what this basically depicts is the supply curve of electricity for a particular hour. And the curve is, as you can see, it's not a nice straight diagonal line as it is in the Economics 101 explanation. In the world of electricity, what the supply curve actually looks like is more like a staircase, you know, of increasing amounts, quantities of electricity that you could produce, you know, increasingly, well, increasing in terms of price as you go from left to right. And then you have your demand curve. In a certain hour, there's a certain demand. As I just said, when we sleep, demand is lower. When, you know, other times of the day, 6 p.m., demand is higher. So at a certain hour, you have a certain amount of demand. And in this particular example, it looks like you would need all of the electricity that you can get produced from your green producer, green 1, from nuclear, green 2, coal 1, coal 2, and a part of the electricity that gas 1 can produce. But you don't need gas 2 during this particular hour, this particular example. So, as you can expect, what the price of electricity would be in this particular hour is depicted here on the red line. And then, this is where the discussions start about, is this a fair way of doing things? You can see in the colored area the amount of money that's going to each of those producers, which actually have a cheaper production cost, but they all receive the same market clearing price. And so the colored area shows what is called in energy economics the infra-marginal rent. It's an expensive word, they say in Dutch. It's an unnecessarily fancy word, perhaps, but it just depicts the rents, the profits, if you will, that they get because they produce at a lower cost and the market clearing price is higher. Now, what would happen if you would say, well, nuclear power plant, you don't deserve to get that price, right? Why would you get the clearing price that is set by the gas power plant in this hour? You produce so much cheaper, so you don't deserve to get that price. You should just sell your electricity at your production cost, and maybe a little bit higher in order for you to get some margin, okay? So let's imagine that the price that nuclear can sell at is depicted at the red line over there, the dotted line with the question mark. What would happen then? Okay, a much, much lower price. I've sort of already explained this in another case, right? So what would happen is you have a much higher demand for electricity at that price, much more willingness of consumers to buy electricity at that lower price of just nuclear, a little bit higher. And what happens then if you let them do their thing? Again, imagine the market, the town square, right, where they all meet, and nuclear is now obliged by law to sell very cheap. Big demand at a cheap price, and so a bidding war starts again, right? And like it was in my previous example with the grains, the price will, during this bidding process that occurs between producers and consumers, will tend to go up until it reaches the market equilibrium price again. That's a dynamic that takes place. The only way in which you could, make something else happen as a state, as a regulator or whatever, would be to say, okay, nuclear, you have to sell at your production cost lower than the market clearing price. And this is the group that you can sell to, a small group that is sort of equal in the amount it wants to consume as what you produce. If you don't do that, much more people want to buy that very cheap nuclear electricity, and you get a bidding war and what I just said. So you would, and that is basically called rationing. The state would not only have to say nuclear you have to sell cheap, it would also have to say, okay, everybody probably wants to buy it at that cheap price, so it's only you guys that can buy it, some segment of consumers or some segment of society, right? That doesn't happen yet in Europe. That's a sort of a deviation from letting the markets do their thing that did not occur so far. Go ahead. Exactly. So that's actually one of the reasons why it's good that it functions in this particular way. When this story happens, the story with just the market clearing price happening, all of the guys with the other technologies see we can make some money. So it becomes very attractive to invest in all of those other things. In the long term, what you expect is a new equilibrium where a lot of investments happen in these other things. And actually, I have a slide for that. Okay, let me come back to that. I want to say one more thing. I told you before that the electricity price fluctuates heavily from hour to hour, right? And now we can show in this figure why that is. If for example, during a particular hour, the demand is much lower, right? I shifted the yellow line to the left. That may depict, for example, that it's nighttime and we consume less electricity. We're less willing to consume electricity at each price. Then what might happen is that we no longer need coal 2 and gas 1, and the new market clearing price during that different hour when demand is lower would be much lower. And also the inframarginal rent that the others receive is much smaller. So fluctuations in demand that naturally happen every day from hour to hour is one of the things that lies at the origin of fluctuating electricity prices that each day. Another thing, and now I'm coming back to you, is this, right? If you suddenly get a much larger quantity of electricity that could be supplied from some green technology, like windmills or whatever, it pushes all of these blocks to the right. You get a new supply curve, and for the same demand, this is now the same demand as the original one, you also don't need the gas plant anymore, and the price actually becomes this much lower. So to conclude, why do electricity prices fluctuate from hour to hour each day? Two reasons. Our willingness to consume fluctuates every day on a national level, also on an individual level. You don't just consume exactly the same amount of electricity all the time. And the production of electricity from some technologies that are dependent on the weather, wind and sun, they fluctuate so much from hour to hour that the supply curve stretches and contracts every hour, resulting also in a different intersection of demand and supply, and hence a different clearing price. Okay, now one last thing. Why would it necessarily be the case that a fluctuating demand for electricity throughout the day leads to a fluctuating price for electricity? Because if we think about it, there are other things that also have a fluctuating demand throughout the day. For example, we demand much more coffee in the morning than in the evening. And so the coffee demand spikes each morning, and beer demand spikes each evening. And there's not so much beer demand in the early morning hours. Well, maybe the very early morning hours there is, but not around 8 or 9 o'clock. So these commodities, these products also have spikes and reductions in their demand every day. But the reason that the price of those doesn't change heavily from hour to hour, beer is not sort of much cheaper in the morning than in the evening, and neither is coffee, right? The reason is that you can store those. You can just easily keep some coffee on the shelf and some beers in the fridge, and in the supermarkets can just be stored across time. But that's the crucial characteristic of electricity that leads to the fact that the price needs to change from hour to hour all the time. You need to produce in every hour, in fact in every second, exactly the right amount of electricity that is being demanded at that moment. If you don't, the electricity grid sort of collapses and you get one of those blackouts. So coming back to my point of we use markets to avoid New York skyline in a blackout, right? We know that electricity cannot be easily or cheaply stored on large scales today, and it's unlikely that it ever will. And so this results in the fact that prices have to fluctuate very sharply. And so this is just a real example here on the left. Some day, random day in September last year in the Belgian wholesale market for electricity. The orange line shows for one day how the electricity price fluctuated. At a certain point in the afternoon, it was only 40 euros per megawatt hour. It's a very large amount of megawatt hour. And later that evening, it was almost 10 times as high. And the typical consumer is not exposed to that, right? You just have your contract with your energy supplier. It says this is the price you pay per unit of electricity that you consume. And as I also already briefly alluded to, this is changing. So it is now becoming possible, by law, it's obliged that it becomes possible, that you have access as a consumer to the option of taking a contract which just follows these hourly price fluctuations. Why would you want to do that? Well, maybe you have, an electric car that you have to charge each day. If you can have a contract with these fluctuating prices, then you can really play a game and make sure that you charge your car during the hours of the day when the electricity is the cheapest. And you may save on your bill that way, in comparison with just having a contract with a fixed price, no matter when you consume. Same with heating your home using a heat pump, which consumes electricity, instead of burning gas. You could then say with your heat pump, oh, I take one of those dynamic contracts with hourly fluctuating electricity prices, and I make sure my heat pump makes the most heat and consumes the most electricity during the cheapest hours of the day. And that's typically when the most wind and sun is happening, and when you have a lot of renewable electricity production. That's when prices get cheapest, as I explained before. And so that's also nice, because then you sort of, through those dynamic contracts, you will have more and more consumers that adapt their consumption of electricity to the hours of the day when there's a lot of wind and sun, which makes things match better. Okay, so I'm going to close with 2 more slides that just briefly give you some takeaways to take home and to wrap it together. This part about how the electricity market works. I explained to you that it basically happens like other commodities, grain and oil and others, using marginal pricing. So the market clearing price is set by the most expensive producer that you need. And there are a couple of misconceptions that I want you to avoid. For example, this year it will be in the media quite a lot. I'm certain of that. The discussion is now happening at the European level to maybe change things about the electricity market. And one of the things that's being questioned is, should we change marginal pricing? So this way it works that I just explained. And so it's important to not make these 4 mistakes about marginal pricing when you think about it. One of them, number 1, marginal pricing is some kind of an artificial thing that somebody decided once upon a time that this is how we're going to do electricity markets. And now that's just a rule that we can just change, and why did we ever decide it that way anyway? That's a misconception. So this way of pricing electricity is not one of many sensible ways of doing it, like a menu between which you can choose. It is just the way it happens when you leave consumers and producers to do their thing. It is also, well, and differently put, it is the only sort of way of organizing a market for electricity that underpins the market equilibrium, right? If you deviate it and do some other pricing mechanism, you'll have undersupply or oversupply or some other mismatch that leads to rationing or to some other kind of chaos. Second misconception, that it would be unique to electricity markets. So as I think, right, explained in an exhaustive way, marginal pricing is something that you see in every commodity market, basically. Beer, coffee, grains, whatever, oil, all of those things. Microchips, solar panels, they all apply marginal pricing. And then the third misconception is that it would be that marginal pricing would be somehow something that is being prescribed, that it would be something that economists say that, oh, we need to do it that way. We express, we prescribe that the market, we want it to work that way. We say it should work that way. That's a misconception. Marginal pricing and the whole, right, the pricing the dynamics I explained, marginal pricing is a description of what happens when economists stand back and they look at the town square with consumers and producers meeting and doing their thing, and they come at some certain quantity and price. We describe what happens there. Apparently what happens is that marginal pricing happens. The most expensive producer that's being used to meet demand sets the price. It's a description. It's not a prescription. And then finally, you may hear some people say this year in the public debate about this, oh yeah, due to marginal pricing in the electricity market, electricity prices are always coupled to the gas price. So it's bad because, some people will say it's not a good thing that electricity prices are so much determined by whatever the gas price does. And in fact, it's not true. As we saw in my example of how the electricity price fluctuates from hour to hour, during certain hours, electricity is much, much cheaper than it is to produce electricity with a gas plant. That means in those hours, we don't need gas plants to meet the demand for electricity. So there is in no sense a strict coupling that, electricity price equals gas price times X or something. There's no formula like that. that says that electricity price should always be some factor of the gas price. It's just that depending on the changing conditions from hour to hour, some hours we need gas prices, and during those gas plants, and during those hours, those gas plants set the electricity price. But as we expand renewables and do other things, we will see less and less hours in which we need gas power plants to meet total demand. And so the coupling, as it's talked about, between electricity prices and gas prices will weaken. And it will at some point sort of decouple, right? And then the final slide, just no longer misconceptions, but actually the correct things to remember. Marginal pricing, that's so being applied in the world of electricity markets, but also in other commodity markets, is a basic principle in economics. It's not something economists say it should happen like that. It's just something we observe that it happens in markets that do their thing. It's applied in all commodity markets, and it in the specific case of an electricity system, it also gives an incentive to each producer of electricity with their own technology to bid into the market their own bidding price that is just equal to their own production cost. They say, I'm willing to produce at my marginal production cost. And that's due to the marginal pricing system that they do that. If they would, for example, receive whichever price that they bid, that could be an alternative system, then they would be very strategic about which price they bid. And they would not necessarily bid at their real production cost, which they do in a marginal pricing system. Right, I will leave it at that, and I will skip my last part about do we need gas power plants. So thank you very much. This took a bit longer than expected. Let's see. Okay, 2 hours and a half, not too bad. Feel free to contact me.